Homework 6, problem number 4. A 500 kilometer transmission line has the distributed parameters or transmission parameters of series impedance equals 0.08 plus J 0.6 ohms per kilometer, and shunt admittance equals J4 e to the minus 6 Siemens per kilometer. We're asked to calculate the sending end voltage and power if the line supplies a 200 megawatt load at 0.866 lagging, and the voltage supplied load is 345 kV on a line-to-line basis. So the line length L is greater than 240 kilometers, right? 500 is greater than 240. That means this problem needs to be solved using what we call the distributed parameter model, or the long line model. And we analyzed the long line model in class. What we saw was that there's two governing equations that result from that. That is that the voltage at the input end, or the sending end of the line, is equal to the voltage at the receiving end of the line times the hyperbolic cosine of the complex propagation constant times the line length, plus the current coming out of the line at the receiving end to the load, times something called the characteristic impedance of the transmission line, and then we multiply that by the hyperbolic cosine of the complex propagation constant times the line length. So that gives us the voltage at the input end to the line. Vs is the source. That's what S stands for, source. Is is the input or source current to the line. That's equal to the output or receiving current of the line times the hyperbolic cosine of the gamma L product, plus the voltage at the output end or load end of the line, divided by the characteristic impedance of the transmission line, Z sub C, times the hyperbolic sine of gamma L. So those are the governing equations for the transmission line. They do introduce two new parameters for a T line that we need to calculate. That's gamma. It's that symbol right there. It's the complex propagation constant of the transmission line. It is found from the square root of the product of the series impedance and shunt admittance on a per unit basis, or on a unit length basis. So that's gamma, complex propagation constant. The second is the characteristic impedance of the transmission line. It looks pretty similar. It's also solved from a square root, but this time it's Z prime over Y prime, so the square root of the series impedance per unit length on a divided by the shunt admittance per unit length. So that's the setup. We just need to solve, basically plug and chug for those equations. These problems get a little bit difficult because of the math steps involved, so make sure to take your time and double check your answers. I like to start by solving for gamma, the complex propagation constant. It's equal to the square root of Z prime times Y prime. So those were given in the problem statement as 0.08 plus J 0.6. That is ohms per kilometer for both of those. Notice that the reactance has been given to you for that series inductor instead of just the inductance. Makes the problem just a little bit easier to solve. You don't have to calculate the 2 pi FL part yourself. It was already done for you. So anyway, now we need to multiply that by the shunt admittance. That's G plus J omega C, which in this case was J4 e to the minus 6. The problem statement gave those units in Siemens per meters. You should be able to convert real quickly to Siemens per kilometer converts over to mhos per kilometer. They're just different units for the same thing. I use Siemens in the text because I cannot figure out how to type mhos in the textbook, so we're stuck with the capital S there, just because I can type it. So you can see from the units that the mho and the ohm annihilate one another, the kilometers multiply by one another, so the units here under the radical are 1 over kilometer squared. So then we take the square root of that, and so we get 1 over kilometers for the units for this. So if you type this into your calculator and you're in rectangular mode, this is what you're going to get, 0.08 0.0000103 plus J 0.001553, and we know that is per kilometer. So that is the complex propagation constant in rectangular form. Because of the quirks of most commercially available calculators, we can't use this number in rectangular form. I mean, this number is correct, but it just isn't usable by, for example, my TI-89. So what I need to do is I need to convert that number over to phasor domain, exponential phasor domain. So I do that in two steps. The first thing I do is I convert the rectangular number into a polar number, 0.001556 at an angle of 86.2 degrees per kilometer. So that's my polar calculation there. And I still can't use that. We have to convert that degrees into radians, and that means that the complex propagation constant is equal to 0.001556. And remember, when you're in radian mode, we tend to write the phasor in exponential format, where we write e to the j, and then we need to convert that 86.2 into radians, and so you multiply that by pi, divide by 180, you get 1.5042 rads per kilometer for the complex propagation constant. So I do encourage you, when you're calculating gamma, to go ahead and put it in exponential phasor form. The next transmission line property we need to calculate is the characteristic impedance. That is equal to z prime over y prime to the 1/2, so it looks really similar. So that's going to be 0.08 plus j 0.6 ohms per kilometer divided by j 4 e to the minus 6 mhos per kilometer. Need to take the square root of all of that per our formula, so there you go. You'll notice in these units what happens is, because the mho is in the denominator, it flips, and so and since kilometers is in the denominator of the denominator, it flips, and so the 2 kilometers cancel out, and then the ohm multiplies by inverse, or 1 over mho, and you get ohms squared, and then we take the square root of that, so the unit of z sub c turns out to be ohms. If you do this calculation, you're going to get 388.154 minus j 25.763 ohm for the characteristic impedance. The calculators can handle that. We don't throw it inside a hyperbolic function, so we don't need to convert that over into any different complex form. We're fine with it in rectangular. So that gives us the characteristic impedance and the complex propagation constant. Next, we just need to solve for the receiving end current and voltage, so that we can plug that into the formulas. So the receiving end voltage, on the receiving end, it was stated to us, but it was on a line-to-line basis. For these calculations, we need it on a line-to-neutral basis, so we just take that magnitude and we divide it by the square root of 3 to go from line to line to line to neutral. And so that's 345 kV over the square root of 3 equals 199.2 kV. And usually we go ahead and we assign that value, the angle 0, make the line to neutral value at the load our reference voltage for these calculations. It is an arbitrary choice, but that is fairly commonly done. The next thing we need to do is calculate the receiving end current. In this problem, it wasn't given to us directly. We were instead told what the power consumption and power factor of the load are. So we know that we can solve the receiving end current if we know the load voltage, the load apparent power, and we divide that by the load voltage on a line to neutral basis, and we take the complex conjugate of that. So we weren't given load apparent power, we were given real power, but this should be old hat by now. We're going to take that 200 megawatts P. First we need to convert it from a three-phase number to a single phase number, so on a power basis you do a div 3. And then also to convert from P to S, we need to divide by the power factor. So that's what that looks like. And then we know that the angle of that is going to be the inverse cosine of the power factor. And then we need to divide that by 199.2 e to the third at an angle 0 degrees. And we take the complex conjugate of that value right there. So that gives us the receiving end current equal to 386.457 at an angle of negative 30 degrees. Amps is the current flowing into the load on a per phase basis. Okay, so now we are ready to solve these equations right here. I'm going to give you another little tip, is that I like to solve for the cosh and the sinh terms separately. I think that's a little bit easier to do than to make this into one big equation. So do yourself a favor and chunk this down, solve for the cosh and the sinh independently. It's just a little easier on the calculating. You might give up a little bit of accuracy if, since we're copying and pasting from different parts in our calculator to do this, but that's okay. So the cosh, if you remember, that we're going to use is the cosh of the product of the complex propagation constant and the line length. So this is going to be equal to COSH. I calculated the complex propagation constant earlier in the problem statement as 0.001556 e to the j 1.50452. So that's in the exponential phasor form, and remember that was per kilometer. And now I need to multiply by line length in units of kilometers for this problem statement. I think it was a 500 kilometer transmission line. So you can see the kilometers cancel out in this multiplication, and we're left with no units as the argument for the hyperbolic cosine. So you want to go ahead and throw this in your calculator. When you do so, be sure your calculator is in radian mode, right? That is in radians right there. So make sure that that's the case. My calculator will only compute hyperbolic functions if it's in radian mode, otherwise I get a domain error. But you throw this into your favorite scientific calculator and you should get the number 0.715376 e to the j 0.050508 radians. So that is a unitless number, but we do want to convert it probably over into polar form using degrees, because that's what we tend to think of as electrical engineers is degrees, at least I do. So I just need to convert that 0.050508 rads over into degrees by multiplying by 180 over pi, and if you do that you get the phasor form of the complex number 0.715376 angle 2.89 degrees. So there you go, you have it in polar coordinates instead, which makes it in degrees, which makes it real easy to use. So next for our calculations, we want to calculate the hyperbolic sign of the gamma L product. So that is sinh of the same thing that's up here, 0.001556 e to the j 1.50452 per kilometer times 500 kilometers. So that's the sinh gamma L product. If you do that, throw that into your TI-89, again you're in radian mode. I should get some sort of sponsoring agreement with Texas Instruments. I recommend that calculator so much. But anyway, you get 0.702532 e to the j 1.51842 rads. Again, you need to convert that radian angle into a degree angle. Magnitude doesn't change, so it's 0.702532, and here we get 87 degrees. So now we've got sinh of gamma L and cosh of gamma L. So, excellent. Now what we want to do is finally get around to these two equations that we started with, these two right here. So I'll Control C, Control V those just to save my life a little bit of work, although my mouse is freaking out. I don't know what is going on. Okay, sorry about that, little technical hiccup there, but those are the two problems we want to solve now. A little more white space to be able to do that. Okay, so there we go. I'm going to solve the voltage equation first, so I'll just drag this current equation down here. Alright, so let's tackle that voltage portion of it. VR we solved for earlier as 199.2 kilovolts at an angle of 0 degrees. We then calculated the cosh term right here. So we need to multiply by 0.715376 at an angle of 2.89 degrees. So that's the first half of that equation. And then we get the current that the load was drawing at the receiving end. We calculated that as 330. No, what did we calculate that as? I lost it. Where did I put you? Okay, it's up here. 386.457 angle negative 30. 386.457 angle negative 30 degrees amps. We need to multiply that by the characteristic impedance that we calculated for the transmission line. That was 388.154 minus J 25.763 ohm. And now we need to multiply by the sinh term that we just calculated, 0.702532 angle 87 degrees. So if you do that correctly, you're going to get, for that first term, for the voltage term, you're going to get 142,503 volts at an angle of 2.89 degrees. And then for that second voltage term, you're going to get 105,615 volts at an angle of 53.2 degrees. And so that gives us a voltage to the input end of the line of 225,131 volts at angle 24.1 degrees is the voltage vector there. So that is the sending end voltage on a line to neutral basis. Because this is a T-line, usually that's going to be represented in a line to line. So 225, 131 times the square root of 3 is going to give you a value of 389.938 kV line to line is the sending end voltage. So that's usually how that would be specified in a power systems analysis. Right? So we got the voltage calculation done. Let's go ahead and plug and chug away to get this current calculation done. So all those numbers we already used in the last calculation, so we can just pick them back up. We get the sending end current is going to be IR, which was 386.457 angle negative 30. Now we need to multiply that cosh term, 0.715376 angle 2.89 degrees. And I want to add to that the receiving end voltage on a line to neutral basis, 199.2 e to the third angle 0. Need to divide that voltage by the characteristic impedance of the transmission line, 388.154 minus J 25.763. I then need to multiply that by the cinch term that I calculated previously, 0.702532 angle 87 degrees. So do those calculations. Do that calculation for the top part, and you should get, what did I get? 276.462 at an angle of negative 27.1 degrees amps for that first portion of it. And then the second portion of it, you get 359.747. It's a terrible 747 at an angle of 90.8 degrees amps. And so you get a sending end current of 446.389 angle 52.55. No, you don't. That was a mistake. You get 335.824 at an angle of 44.1 degrees amps. Sorry about that. Read it off the wrong piece of paper. So that gives us the sending end current that we get there. From the distributed parameter model, to calculate power, we want to extract that from the VS and IS on a single phase basis or a line to neutral basis. So the total power in this transmission line is going to be 3, and we're going to multiply that by the voltage magnitude, the current magnitude, and then the cosine of the phase difference between the voltage and the current at the input end of the transmission line. So that was going to be, let me just scroll up a little bit so we can see our numbers. 225, 131 time, oh, I forgot my 3. 225, 131 times 335, 824. So that gives us the magnitude of the apparent power. We want to convert that over to real power, so we want to take the cosine of the angular difference between the two. So that's, what do we get, 24.1 for the voltage, which was our reference, and then we need to subtract off the current angle, 44.1. And so the total power I get approximately equal to 213 megawatts.